This video is on semiconductors. We use the energy band diagram here to describe how semiconductors work. So the first concept is Fermi ionic emissions. And basically what we have is in the presence of thermal energy, when we add thermal energy to the system, bound electrons can break free, and when they break free, they rise into the conduction band. And when they do that, they leave behind a hole. And remember, the conduction band, those are loosely bound electrons. In the valence band, those are bound electrons. So the intrinsic carrier concentration is basically the concentration of these electrons that are generated from thermal excitation and the concentration of holes. Since each electron creates one hole, we have that the electron concentration is equal to the hole concentration, and that is equal to what we call the intrinsic carrier concentration. When the temperature is higher, we add more energy and more electrons break away, so that concentration increases with junction temperature. But if the band gap energy is higher, that means that electrons require more energy to liberate. So as a result, the carrier concentration decreases when the band gap energy is higher. Okay, so now let's talk about dopant atoms. And dopant atoms are basically atoms with partially filled outer orbits. So what you see here, this outer orbit could have had 4 electrons. But in a dopant atom, it has 3 out of the 4, so it's partially filled. Doped semiconductors are semiconductors that are doped with dopant atoms. So semiconductors with atomic impurities, and these atomic impurities are these atoms with partially filled outer orbits. So donor atoms are atoms that have loosely bound electrons. So when added to the semiconductor, what we're essentially adding are electrons to the conduction band. So we're actually putting electrons right over here. Since we're adding electrons to the conduction band, the holes become minority carriers. And let me say this, when we add these dopant atoms, we add a lot of them. So we have a lot more electrons now than we have holes, so holes become minority carriers. And the carrier concentration of holes therefore reduces to the thermionic concentration of holes, or the concentration of holes that thermionic emissions allow. And then when we look at the electron concentration, that's the electron concentration that thermionic emissions allow, plus the number of electrons that are added by donor atoms. But these are so much greater than thermionic electrons that the electron concentration just reduces to the number of dopant atoms that have been added. And let me be more specific, donor dopant atoms. And this is going to be much greater than the intrinsic carrier concentration that describes the thermionic concentration in the absence of impurities. So what we're saying here is that we're taking a semiconductor and we're adding a whole bunch of electrons to the semiconductor, which are negatively charged. So the material is said to be negative, an N-type material, a negative type material. So when we look at the energy band diagram, here we have the conduction band, and in the conduction band we have a lot more electrons, and this here to the left indicates electron concentration, and we see here that we have a lot more electrons than we have holes, and that is to say that we've added donor atoms to the semiconductor. Since the probability of finding electrons is so much greater than finding thermionic holes, then we can use the Fermi level, which, remember, it represents a 50% probability of finding a charge carrier. Well, since we're more likely to find electrons, this Fermi level is going to be closer to the conduction band. So what we're saying here is that anytime we see a band diagram, energy band diagram, where the Fermi level is closer to the conduction band, what we're saying is that it is much likely to find an electron charge carrier than a hole charge carrier, which means that it's an N-type material. So let's talk about the mass action law. Well, if we add electrons to the system, the number of holes that are already in the system are going to tend to combine with those electrons. That means that the hole concentration, or rather the thermionic hole concentration, will tend to decrease. And that's what we're saying here. The whole thermionic hole concentration is less than the intrinsic carrier concentration. And the total hole concentration is basically just this thermionic hole concentration. And as the number of donor atoms increases, then this doping charge carrier concentration decreases, and it decreases by basically this fraction, where we have here the intrinsic carrier concentration squared. Okay, so what are acceptor atoms? Those are atoms that have incomplete valence bands. That means that when added to a semiconductor, they're basically adding holes to the valence band. And that means that electrons in that system, since we're adding so many holes, the electrons become the minority carriers. And if they're the minority carriers, then that means that the electron hole concentration is pretty much just the electron concentration that thermionic emissions allow, which in the presence of a lot more holes is less than the intrinsic carrier concentration, and it decreases with a higher concentration of acceptor atoms. So basically we're just applying the mass action law, but now to this type of material that has acceptor atoms added to it. So when we look then at the hole concentration, it's going to be the thermionic concentration plus the added holes that acceptor atoms are adding. But these are so much greater than the thermionic hole concentration that it just reduces to the number of acceptor atoms that are added, because each acceptor atom is adding a hole, and that is much greater than the intrinsic carrier concentration. So what are we saying? This material has a lot more holes in the valence band, available holes in the valence band, than available electrons in the conduction band. So this is said to be a positive material, or positive type material. So when we look at the band diagram for p-type material, well, we're going to see a lot of holes in the valence band and just a few electrons in the conduction band. So what we see here is the concentration of holes. It's much greater than the concentration of electrons. Since the Fermi level represents a 50% probability of finding a charge carrier, and we're more than likely are going to find hole carriers, this Fermi level is going to be closer to the valence band. And this is how we know that that the band diagram is representing a p-type material, because the Fermi level is closer to the valence band. Mobility. Well, mobility, now that we have these charge carriers, mobility is the ease with which these charge carriers flow when exposed to an electric field. When we increase the temperature, we excite electrons into more mobile states. That means that these charge carriers, it's easier for them to flow. So the mobility, and this is what we use the Greek letter mu for mobility, increases with temperature, with higher temperature, because they're more mobile when the temperature is higher. The other thing that we know is that bound electrons are less mobile. So bound electrons in the valence band, when they see a hole, they move to that hole, but not with the same ease that free electrons move in the conduction band. What we're saying with this is that the mobility of holes is less than the mobility of electrons. Let me say this more into what we really mean. The mobility of bound electrons that move from hole to hole is less than the mobility of free electrons in the conduction band. That's really what we're saying with this. But normally we just reduce it to saying that the mobility of holes is less than the mobility of electrons, and it's usually between 2 and 3 times less mobile. Well, I hope this was useful. Thanks for watching.